When converting the column from a pot to a continuous still, there are several components we need to add: a stripping column, wash infusion pump, steam generator, and a bottoms parrot. I cover the steam generator, infusion pump and bottoms parrot in other videos. Here I will concentrate on the stripping column. All of these components are covered in the plans linked below. The column used in the tight azeotropic pot still is a rectifying column because the process of distilling spirit to a high alcohol concentration is called rectification. All stills require another process called stripping, which is removal of alcohol from wash in order to minimize losses. In a pot still, this is done by boiling the alcohol off the wash, reducing its concentration. At the bottom of the rectifying column, liquid drips back into the boiler, and this liquid has the same alcohol content as the vapour coming off the boiler. For example, with a 10% wash, the vapour and liquid dripping into the boiler is about 55% alcohol. As a batch distillation run progresses, the alcohol content of the boiler falls, as does the alcohol content of the vapour coming off it. At the end of the run, when there's perhaps 1% of alcohol left in the boiler, the vapour contains about 8% alcohol. Starting with a typical wash concentration of 10 to 15%, that results in a wash alcohol extraction rate of 90 to 95%. With a continuous distillation system, we don't have this mechanism of maximising alcohol extraction, so we add an additional column below the wash injection point. That's called a stripping column. Its purpose is to strip as much alcohol as possible from wash to minimise losses to the bottoms. It turns out that with the ethanol water system and wash ethanol concentrations of around 10%, stripping is more difficult than rectification. Commercial continuous distillation systems typically have longer stripping columns than rectification. A commercial column for spirit may be 60 feet high, of which the top 20 feet will be rectification and the bottom 40 stripping. My design of rectifying column operates optimally over a narrow range of vapour flow rates, as is characteristic of packed columns. If we also have a narrow range of operating flow rates for the stripping column, we will have a hard job matching the two columns so that the same power allows them both to operate optimally. That means another packed column is not going to be a good option. We need a stripping column that can operate over a wide range of flow rates. The conventional column that's best suited to that is the bubble cap column, but that's going to get very long and expensive, as we're typically going to need twice the length of the stripping column as the rectifying column. Columns work by bringing liquid and vapour phases close together. They interact slowly, so the vapour and liquid phases need to be in contact for a while. The lower the surface area compared to the volume of liquid, the longer the two phases need to be in contact, so columns slow the rate at which liquid drains down and maximise the surface area of contact using sieve trays, packing or bubble caps. After experimenting with different columns, I developed a sloping stripping column that uses a gentle gradient to slow down liquid movement. It's cheap, short in vertical height, easy to build and operates over a wide range of flow rates. And it is simply an insulated tube sloping downwards at a shallow gradient. It is a 3 metre length of 15 mm copper pipe sloping down at a gradient of between 40 and 50 to 1. For convenience and to make it easier to insulate, I cut the pipe into 4 750 mm sections, then make it into a rectangular spiral or zigzag. It's made of 6 90-degree elbows, 3 pieces of copper tube 20 mm long and 4 pieces 750 mm long. You add wash at the top and steam at the bottom. With this pipe length and gradient, the wash trickles slowly down the pipe, giving it enough time for interaction with the steam. Bottoms drain out via a U-tube, which is a parrot, and an alcohol vapour steam mixture comes out of the top for feeding into the rectifying column. The most significant advantage of this stripping column is its tolerance of different flow rates. You can get good stripping with liquid flow rates from 0 to over 20 mL per minute of 10% wash. The stripping column bottom is a bit more complicated. Commercial continuous stills use a preheater to heat the wash to the temperature of the column, which is about 85 degrees centigrade at the injection point. They also use a heat exchanger, which removes heat from the hot outgoing bottoms and gives it to the incoming cold wash to minimise heat wastage, as energy is one of the main costs of commercial distilling. I've tried both and a preheater is not necessary. The stripping column has a sufficiently wide range of operating parameters that you can add cold wash at the top and increase the amount of steam delivered to compensate. A heat exchanger isn't necessary either. The still runs at about 150 watts, and the heat exchanger will recover maybe 20 watts, so the reduction in power consumption is small, but it does have another advantage. It cools the bottom parrot from around 40 degrees centigrade to closer to 20 degrees centigrade. This makes the temperature compensation necessary in reading the alcohol ABV small and consequently accurate. This turns out to be quite important when you're looking at alcohol concentrations in the 0 to 0.3% range. The heat exchanger comprises a copper pipe which conveys the wash inside a larger silicon rubber hose which conveys the bottoms. At either end is a piece of wider copper pipe that fits the silicon hose, through which the smaller copper pipe passes as shown here. One option is to use 8mm and 3mm copper pipe. Drill diagonal holes through the pieces of 8mm pipe, thread a 600mm length of 3mm pipe through one and solder. Take 500mm of silicon rubber hose, thread the fine copper tube through the middle and seat it in the 8mm piece. Squash the silicon hose down away from the top end connector and solder it. Then seat the silicon hose at the top. This works well but is prone to getting blocked if you're using unfiltered wash. That's not an issue if you're using strip. If you want to distill wash, I suggest using 15 and 8mm pipe as shown below. The method of construction is different because 8mm pipe is less flexible than 3. I use 8mm elbows that require 9.5mm vertical holes in the pieces of 15mm pipe. The whole 8mm elbow will not fit inside a 15mm pipe, so drill 9.5mm holes centered 16mm from the ends. Feed in the elbows from outside and solder. Then solder short 8mm pieces to the elbows outside to connect the hoses for wash. Take a 500mm piece of 8mm pipe and solder it to one inside elbow end that should be flush with the end of the 15mm piece as shown. Add the silicon hose and squish it down to solder the other end. The column bottom needs ports for vapour flow up into the stripping column, bottoms to exit and steam to enter, and a thermal well for a temperature sensor. Steam enters at the bottom and bottoms exit about 15mm above, so that the steam bubbles through the bottoms to achieve temperature equilibration. The thermal well dips down below the bottom exits port, so the temperature senses of the equilibrated bottoms and steam, which will give an indication of alcohol content. The whole thing, including the heat exchanger, stripping column bottoms and stripping column, are insulated. Steam is added to the bottom of this stripping column. Wash is added to the junction between the stripping column and rectifying column. Bottoms are taken out via a U-tube from the bottom. I recommend using a precision bottoms parrot as this U-tube. The top of the stripping column is connected to the bottom of the rectifying column with a 15mm elbow and a 15 to 28mm copper reducing fitting. When those two parts are soldered together, drill a hole into the vertical part of the elbow and solder in a short length of copper pipe. This is where the wash is injected. The diameter isn't critical, and if you're using straight wash, particularly if it's not filtered, I would suggest using an 8mm piece of pipe for this, as well as the copper core of the heat exchanger. Otherwise 3mm is fine. When the column is operating optimally, the pressure inside is slightly higher than atmospheric, being about 150mm of water at the bottom. Tuning the column involves larger pressure swings. If you use a short U-tube, the liquid will be blown out of it by vapour pressure, and the vapour will then flow out so fast that the liquid can no longer accumulate in the bottom, stopping it from working. To prevent this, use the bottom's parrot as a U-tube. It's deep with a narrow inlet side and a wider outlet side to accommodate a hydrometer. The outlet side is open to the air, making it ideal for this purpose. In the next video, I will return to the question of still control.